we talked about convolution last time, and I have a little demo that your TA Sci made for the class, and that is to just do some two-dimensional convolution. Okay, we defined what convolution was. We saw it was a local averaging. Here's a stock image used in image processing a lot, and what he did was he said, well, let's add some noise. So he adds random noise to this image, you can see, and then applies a small local averaging function, which is a convolution, to this image just to see the consequence. So here what we have is all it's done is average the neighboring pixels. So it just takes the pixel at the center and each of the 8 neighbors around it. It does an average. In fact, we can see what the average function is. It's defined right here. He takes 1/16 times each of the neighbors and 1/2 times the value itself and does that average to produce the output. Now, how do you do this? You just use the convolution command. There's a built-in conv2. The 2 there just means it's a two-dimensional convolution. So now we know what convolution is. We see it's very easy to apply this sort of process to a signal. Of course, we've only talked about one-dimensional convolution, and the difference here is very straightforward. It's simply that our convolution in one dimension was, we shift this weighted average function to every possible output value and do our multiply and sum. And what you're doing two-dimensionally is you're shifting, both directions, all possible shifts, and doing the same calculation to produce the output. Okay. So, like I said, we won't really look at the math of two-dimensional signal processing, but it's just the same thing as the one-dimensional stuff that we're talking about. Now, we could change. I hope you can see the difference between these. On the projector, it's not quite as pronounced, but this one it's a little. The projector does its own smoothing, I think. So you don't see quite the same as what I see on my screen, but you see it's a little bit different. But what we could do is try a different averaging. So, for example, we could go to a wider swath, make our function h that we're convolving with be bigger than just 3 by 3, and that would give us more averaging. Instead, let's try something like this. Let's make it not be square. So let's say h equals, we'll do something like make it wide but not vertical, just a vector. Okay, so I'll get the 4 neighbors in each direction. I'll weight the middle one higher. Okay, if you notice here, so I have 4 in each direction, and the middle one's higher. These don't sum to 1. Of course, it doesn't matter whether they sum to 1 or not necessarily, but let's just divide by 2/3 or multiply by 2/3 so that it does sum to 1. Okay, so this is truly an averaging. That way, the output image doesn't have intensities that are too high that get cut off by the rendering. Okay, so this. So here's an averaging. What do you expect if I convolve this? So think of this. This means our two-dimensional convolution is just very wide and not tall. Okay, so just using whatever intuition you have, what do you think is going to happen when I do with a convolution here? No idea? Well, we should get smoothing more in the horizontal direction than the vertical direction. So let's see if we notice anything here. So again, there's the noise. Here's the output, and it's a little bit subtle, but there's more smoothing horizontally. Vertically, you still get some ridges. I'm wondering with the projector whether you can really see that. It's sort of a neat effect because it looks like you have some grain of your film that's horizontal or something like that. Okay, because we've just done smoothing in the horizontal direction. All right. Great. So we know the mathematics of discrete time convolution. This is a discrete time signal because we have pixels at particular points. Let's now do continuous time convolution. All right. Actually, I'll write both of them down for comparison. Convolution, we have discrete time. second. All right. In discrete time, we would say x convolved with y of n equals the following: x of k, y of n minus k. And in continuous time, it's the same formula pretty much. X convolved with y, assuming they're, whoops, not plus, convolved, assuming they're continuous time signals, is an integral from negative infinity to infinity of x of t, or let's say tau. Sorry, we need a variable for integration. Y of t minus tau. Remember, tau is just the variable for integration. T is the variable of the output signal. Okay, it's the domain of the output signal. So it's what you'd expect, same formula for continuous time convolution. Now, all right. Now notice that I've changed notation on you. Did someone notice that? This isn't exactly how I expressed convolution in the previous lecture. Before I was saying, so it's often that this convolution between two signals that I'm writing right now this way is often written as x of t convolved with y of t, and that's how I was writing it previously. Okay, and in fact, I'll use that a lot here. However, it's really an abuse of notation. This one here is not a precise way to write what we mean. There's a reason for it. First, I'll tell you why it's convenient. Why would we do it that way? Okay. So it's well. I'll explain in a moment what's wrong with the notation. But the thing that's nice about it is we can concisely write statements like the convolution of manipulated signals. Manipulated, I mean, think of the manipulations we've talked about recently, like doing a time shift or a time scale. If we want to say, take x, the time-shifted version of x, and convolve it with, let's say, a time-scaled version of y for some x and y, that's a very simple way to, it didn't take much for me to write down, and you know what I'm talking about. All right. So that's nice and simple. If we didn't use this notation, if we use the notation on the right, the notation on the right, on the left here, the one I'm saying is more mathematically precise, is saying convolve these two signals, and the result is a function of t. That's why that's what this notation means, right? And so under that more precise notation, if we wanted to do the above, we would say, so without this notation, you would have to define a new signal, x2 of t, and make that equal x of t minus cap t. All right, and define a new y2 equals the time-scaled version of y. And then you would say, take the convolution of x2 and y2, okay, which is a signal of time. It just took a little more writing. All right, so that's really the main reason why we would use this notation above. Now, what's wrong with it is, convolution, the result of the convolution is not just a function of x at a particular point in time and y at that same point in time. This notation implies that for a particular t, you just look at x at time t and y at time t as the inputs to this convolution. That's not true at all, right? So convolution depends on the entire signal. for each output time t. So this will lead a few of you to confusion if you don't internalize it right now. You'll say, oh, I want to evaluate the output at a certain time. I'm just going to look at x at that time and y at that time, and then you're trying to figure out what operation you're doing to calculate it. It's not going to work. You use x for all time, y for all time, to calculate the output at any one time, right? Also, if you try to say, oh, I know what if I shift the inputs? So I do a t minus cap t for both of these guys. And then I take a convolution. And that type of thing is going to be confusing as well. Because, again, this notation is just, well, it's incorrect, but it's convenient. All right? So don't try to do things like say, oh, I'm going to do a time shift for the convolution. That's going to mean I replace every little t with t minus cap t in this expression. That's not true. Because if you do a time shift on x and a time shift on y, you get a convolution that's shifted a different amount. All right? So just remember what this actually means. We do an operation on the entire signal, and just, the only reason we're putting a t here is so we can have an easy way to express new signals concisely. Okay. All right. Next thing. I'm going to introduce actually I have a little demo on online here. This is Wolfram. They have a little page on convolution, and this is just emphasizing the flip and shift technique that we introduced last time for calculating convolution. Here they're showing what are supposed to be continuous time functions. It's the same operation for doing a convolution, right? What they're showing here, and I can't pause this, but just this is the convolution of the red function, this red signal, and this blue function where y is supposed to be the center of, y is the x equals 0 line of that blue function. It keeps moving, but just imagine it's some stationary function. It's another rect, all right, centered around this vertical y is the 0 point, okay? And what they're doing is they're calculating the convolution between the red and the blue functions. And to do that, remember, you take either one of them, because convolution is symmetric. You first flip it in time. Now, both of their examples here they're doing two rects convolved, and here they're doing two Gaussian functions convolved with each other. Okay, either one of these are symmetric, so the flipping in time is irrelevant for these particular examples. But then what they do to calculate the output signal for any point in time is they have to shift one of these. It's the blue one in this case. They shift it to the point in time they're trying to calculate. Okay, so here they're just showing all the possible shifts. And notice when there's no overlap, they should get 0 as the output of the convolution. So the green line is showing the output function. This green is the output. And it's 0 once they stop overlapping. Okay, so it's like imagine they're drawing this output as this green line passes each point. Now, how are they calculating the output value? They're looking at the product of these two functions. That's the gray. The gray is the product, okay? And they're integrating it. So you see 0, 0, 0. It's increasing now. It's full. That's the highest it gets. It decreases, and it's back to 0. All right, so that's the convolution. So you can go online and look at this yourself. Here for the Gaussian, for this function, same type thing. There's not really much overlap, so it's basically 0. Now there's some overlap. You see this gray is showing the product of the blue and the red. And what you really need is the integral of that product to calculate this output value, which is that green curve it traces out. Okay, so a couple things to note. Of course, in all the examples we've done so far, we've only convolved non-negative real functions. Okay, notice both of these are positive, and whatever. They can be anything. They can have negative values. They can be complex. So when you actually do the calculation, maybe some parts of the integral cancel other parts. Okay, it's clear from the mathematical expression, but it just hasn't showed up in any of my examples yet. Also, of course, in continuous time, you're not going to go through like you did in your problem set. In your problem set, you have very simple discrete time signals that you convolve. And you go through one at a time of the output, and you just add things up and calculate the output like I did in the lecture last time. You're not going to do that in continuous time. There's too many outputs times, right? You're going to have to find a formula. You're doing an integral, and you're going to have to just, calculate the formula for what the output is at each time. And sometimes that's going to involve solving different cases. The case when they overlap, the case when they don't overlap. And you might have to look at a few different cases, and in between certain time intervals, you'll get a nice expression for what the output convolution is. But then when you get to a new point in time, you're in a new setting where the overlap has changed, and you calculate a new integral. Okay? So now we're going to introduce the continuous time delta function. And this is called the Dirac delta function. Remember that I introduced a delta function last time, the discrete time one. It's the Kronecker delta function, and this is in continuous time. So you might hope this is just going to be as simple as the discrete time one. It was about the simplest function we could think of. To remind you, in discrete time, we had delta of n just equaled 1 if n equals 0, 0 else. We could have said it was the indicator function that on the set 0. The indicator function that n was in the set 0. That would be another way to write the Kronecker delta function. Okay. For continuous time, that a function defined that way would not be useful. All right, let me try to convince you that. So the delta function, delta of t, that we define is not actually a function. So this is why we're going to dedicate part of a lecture to talking about this thing. You define it by how it behaves in the integral. So we're going to define this function such that if you integrate the delta function times some other function, dt, that you get the value of that other function at 0 if f is continuous at 0. At t equals 0. Now, notice, if you look back in your notes, this is just the shifting property. So we have a shifting property that if you do this Kronecker delta function in discrete time, that property holds, and it's easy to verify. We want a function where that same property is going to hold in continuous time. Okay. Now, of course, once you have that, then you have the generalization of the shifting property, which is that, let me write this again. So shifting, usually we want to express it slightly more generally, although really this is just a change of variables. And we say delta of t minus cap t times f of t dt is the value of f at cap t. If f of t is continuous at t equals cap t. Okay. So what we're saying is, so often what we're saying is that if we multiply, here's t, here's some signal. Let's say here's a signal like this. Now what we usually do is we express, so this here is f of t. We usually express a delta function as, the way we plot it is we put a little vertical arrow at the location of the delta function. So in other words, if we have f of, let's say, this is cap t, and this function here is f of t minus cap t. I say the location is cap t because we usually think of a delta function as something that occurs at time 0. So then f of t minus cap t should occur at time cap t. Okay. So this is the way we would draw it. I haven't really, we say there's some vertical arrow there. That's our delta function. And what we want is that if you multiply these two things, and we would actually say it has a height of 1 because the delta function does. And when we multiply these two things, in fact, let me scale things differently. Let's assume that that's not f, that's delta. When we multiply them, we get something here. That value of f of t times our delta should sort of rescale it. And we want to integrate, and we want the result to just be the value of that function at that point. Okay. How should we think about this? I mean, I want to convince you, first of all, that there is a natural way to think of this delta function. I also want to convince you that it's not a real function. You couldn't come up with a function that gives you this property. Okay. So let's start with how to think about this. So it's like a short pulse. Okay? So think about, what if you had something, it's not our delta function, but it's this is going to be an approximation to our delta function. It's going to have a variable, capital delta. All right? And we'll define this to be a rect, but that's time scaled to only have width delta, with capital delta. Okay? And it's also going to be scaled vertically so that it's, the reason for that is I want it to have an integral of 1. Okay? Rect by itself has an integral of 1, but if you time scale it, the integral changes. So I'm scaling it vertically as well, so it still has an integral of 1. All right. So this thing here is just, of course, we have centered around 0. We have something like this. All right. And the height is 1 over delta. And the width here is delta. So it goes from positive delta over 2 to negative delta over 2. Just a little pulse. And we want to imagine delta being very small. So this is a tall, narrow pulse. That will be very much like this Dirac delta function that we've defined. Okay? Because notice that, let's look at, we can make a precise statement about when you take an integral here. Okay. If you take the limit as delta goes to 0 of the integral of delta of this thing, dt, then this is going to actually equal f of 0. Again, if f continuous at t equals 0. Okay, so let me convince you that that's true. The two functions we have here, we have our f, which is something like this. Okay, we have, that's f of t. And we have this delta function, which again is this tall, narrow thing. Okay, so that's our delta for some small value of t. All right. Now, if that value is small, then we know that f is going to be approximately flat. You know, you can approximate f as being flat here over that interval. You can approximate it by having the value of f of 0. Okay, and if it were truly flat, now this integral would be very straightforward because the product of these two things would simply be, so the product is approximately, so delta of, so this thing here approximately equals rect t over delta, that function, times f of 0. Okay, because that's how we've just approximated it for small delta. And now we can integrate this. So you integrate this, of course, the second part is just a constant. You get f of 0. All right. This was only true because f is continuous there. If f was discontinuous, you wouldn't make that approximation. So that's why we always have this condition. All right. So really, that's what we want. We want a very short pulse, but a pulse that still has area 1. All right, unit area. And that's our Dirac delta function. So does anyone think that we could actually just take, I mean, is there a function that would give us this property? We seem to almost have one. We've got this thing. So a lot of people like to say, you know, so it's, you can incorrectly claim that that you could take the limit of these functions. The limit as delta goes to 0 of this thing. All right, that's sort of tempting to say that, but that's not actually true, because if you take that limit, well, you're going to get the limit as delta goes to 0 is going to be 0 for all values of t that are not 0. There's going to be infinity for t equals 0. And then you have to know, how do I integrate with an infinity there? And under most definitions, that wouldn't even matter. The infinity doesn't matter because it happens at a single point. And so this is just going to be like integrating the function 0. Okay. So it's actually not going to behave like we want. And even if you had you defined some weird way to integrate this that gives you something non-zero, you're still going to have the problem that, what if we scale a delta function? That should give us a different answer. And yet you can't scale infinity. Okay, so this is not a workable definition. All right. And another, for those who are interested mathematically in looking at this integral, there's another important reason why this limit is not this is not a useful integral for our purposes, and that is that the function doesn't, even though it does converge to this function, it does not converge in L2. And if that means something to you, great. This in other words, the error between these delta function approximations and this final limit, the error blows up under the L2 norm, under the energy. Okay, it goes to infinity. So this limit is not going to do anything nice for us. Okay, so that was maybe more technical than many of you care for right now, but the important thing is we're going to make good use of this sort of pseudo function, this delta function that really it's not a precise function, but we're going to have a way of plotting it using these arrows, and we're going to have a way of integrating with respect to it. Now there is a way to make this mathematically rigorous, but it's not by defining a function. It's by using a more general form of an integral. All right, so you can integrate with respect to measures. And the integral that we know from high school calculus is to integrate with respect to the so-called Lebesgue measure that puts equal weight everywhere. If you integrate with respect to another measure, that measure can have a point mass on certain places, and you can make all of this completely precise. But we'll leave that to an analysis class. Okay, and we'll be able to do everything and get all the same answers just by using this idea that there's a delta function that gives you this sifting property. Okay, so let's look a little more at this delta function just so we know how to use it. So let's see. So here's a convenient substitution that you'll sometimes find. we will say that a function, here I'm going to, we always are going to assume it's continuous at the location of the delta functions. Otherwise, we don't have anything well-defined. F of t times a delta function at a particular location, okay, we can make the substitution that we can swap that first variable t for the constant t. So this is sort of like saying the delta function is basically 0 everywhere except its location, cap t. And since it's 0 everywhere else, we don't actually care about the function values for other points. They don't matter. Only the function value at the delta function matters. And so this substitution is okay. Sometimes it simplifies things. Now, to check if any of these rules are actually valid, you just have to say, is this true under the integral? Because we only care about what happens to the delta function under the integral. Now, often I mention this sort of statement. I say we only care what happens under the integral. I think I've said the same thing when I said in continuous time we don't care about moving an isolated point of your signal. The reason is that think about convolution. That's going to be an important process that we care about. Convolution is an integral. All right? Think about the Fourier transform. The Fourier transform is an integral. Therefore, if we do things, if we know how something behaves under the integral, then that's usually all we care about. Okay? And so when I say you can make the substitution, let's check. If we integrated the right-hand side, we know by sifting the left-hand side, we know by sifting property that that's just f of cap t. But we can expand that out. If you integrate the right-hand side, it's trivially f of cap t, because this right-hand side, this first part is a constant with respect to the integral. So you can just pull it out, all right? And then we're just saying, what's the integral of the delta function? What is the integral of the delta function? It's 1, okay? Why is it 1? Well, I guess sort of inadvertently we defined these approximations to always have integral 1. But also, sifting property just says that a delta function times anything is the value of that other function. So this, let me write it out, f of cap t integral of delta t minus cap t dt. If you want to know that that's 1, just pretend there's a 1 here. We have a constant function 1. Therefore, sifting property says the integral is 1. Okay, so something to remember. Actually, I'll write that down. It's probably an important thing to remember. The delta function has integral 1. Okay. Now, all right. Let's, that's one substitution. I'll put a number on it. There's 1. Here's another substitution in the delta function that will be convenient. What if you timescale a delta function? Okay. Does anyone have now some intuition? Remember, think of the delta function as a very narrow, tall rect with area 1. If you timescale it, what do you think it might be? Nothing happens. So you're saying it's still delta t. And that is close, and maybe the most natural guess. There's something else going on with the timescale. It's a little hard to guess, I think. Does anyone have a guess at how it changes? It's almost equal. So imagine. Yes, we need to integrate to the same thing. So notice that if you timescaled any one of these approximating rects, you change the area. So we need it to, so we can say, yes, it's delta t, but divided by the absolute value of a. Okay, so it gets scaled vertically. That's a very weird thing, right? We do a time scale on a delta, and it doesn't change because location doesn't change. But it gets scaled vertically to keep the area the same. So we'll check, and maybe by checking, you'll see, let's check it right now. To check this, we say, okay, we want the integrals to be the same. So let's do this. Delta of at dt, and let's do a change of variables. So let's let tau equal at. Then this equals the integral. The limits don't change because we're well, the limits change just like before. We'll check, the limits will flip if a is negative. Okay. For now, just kind of pretend it's positive. Then we get a 1 over a delta of tau d tau. The 1 over a is from the change of variables, right? Now let's take into account if a was negative, then the limits of integration would have flipped. That gives us a negative sign out front. The double negative makes this an absolute value. Okay, so, and then of course, now an integral of the delta function we just said is 1. So this becomes 1 over that. But the important thing is we could actually just put it right back in. I mean, you could just say, you could put that 1 over absolute value of a back in and say, oh, look, delta of at acts like 1 over a delta of t under the integral. Okay, so the integral of this is 1 over absolute value of a, and clearly the integral of this right-hand side here is also 1 over absolute value of a. Okay, so but if you need some intuition, just think about you timescale these rects. Okay, they now have a new area. Let's use this idea and also say, what if we have so then what if we actually had like x of t equals delta of t minus 3, so no longer centered at 0. Okay, so that's this thing. T 3, 0. So we've got this height of 1. That's just the constant that goes on the delta function. And now if we do a time scaling on this, let's look at x of, say, 3t. Well, we know time scalings are that's going to shrink the horizontal axis. Okay, so our delta function is going to move. It's no longer going to be at 3. It's going to be at 1. All right, that part's easy. We know how to manipulate signals that way. So we have a delta function here, but the tricky part is its height changed as well. Its coefficient is not 1, it's 1/3. Because we're using the property above that when you do a time scale by 3, you get a 1 over 3 out front. Okay, so and actually if we express this way, we'll see it's exactly, this is going to be delta of 3t minus 3, which is maybe better expressed as delta of 3t minus 1. And we see that it's a time-scaled delta function shifted. We could think of it as a time-scaled delta function that gives us the 1/3, and then afterwards shifted by 1. Okay, so it's exactly what we would expect here. The delta function at this, we could then use our property and say that equals 1/3 delta of t minus 1. There. We arrived at it by formula. Okay. What if, all right, boy, time flies. All right, I am going to move on to something else that's related to what we talked about previously. Part of the reason for doing this is because your entire problem set you could have done by now quite easily. Well, maybe not easily, but you could do with what you've learned. But there are some points I could emphasize, and maybe that will clarify some things. All right. So here's a couple of points. How do you interpret magnitude and phase? We're now going back to Fourier transform mode. So we've been talking about convolution, And you have to kind of go back in time at least to about Monday to get back into Fourier transforms. I guess you've been doing a lap, so you have Fourier transforms in your head. Okay. So magnitude and phase of frequency components. And I'm going to use the Fourier series to emphasize this. So, because I've had some students have asked me this question. How should I think of the magnitude of a Fourier series coefficient, or the magnitude of the FFT? Magnitude is equal to another name you might be more familiar with. It's the amplitude of a sinusoid component in your signal. Okay, magnitude equals amplitude. And phase is a time shift of your sinusoid. Okay, so if we go back, we had an equation in one of the earlier lectures where we said the Fourier series, which is simply x of t equals, it's a sum of sinusoidal components, although the sinusoids are complex exponentials, ak e to the I 2 pi k over cap t, t. And so for particular values of a, you can get back your periodic signal here. But we also noticed, and this is something we did actually mention in one of the lectures, and we will visit again, if x is real, this becomes, there's a nice pattern here where your positive coefficients and your negative coefficients are just conjugates of each other. Okay, so if x is real, this is true. And because this is true, that means that x of t, in fact, can be expressed as a different sum, one that's maybe more natural to think about in terms of cosines. It's harder to work with mathematically, but it's easier to think about. And that is that it's, well, first of all, in this expression, I haven't really changed anything. I've just combined like terms. So I can express it this way, plus a of k conjugate e to the negative I 2 pi k over t. But then using Euler's identity, you can realize that each of these terms is just, this is just a0 plus some sum k equals 1 to infinity of your magnitudes of ak times a cosine of 2 pi k over cap t being the frequency plus the phase of ak. So in this form, it becomes clear, how do I interpret these coefficients? Their magnitude is the amplitude of the cosine, and their phase is just the time shift, not precisely a time shift, it's technically a phase shift of that cosine. Okay, so there you go for magnitude and phase. Now, I also wanted to show you, there's a property that's a, yeah?
So you said that it's a phase shift rather than a time shift. Does that mean that it ranges from 0 to 2 pi?
Yeah, and if it goes above 2 pi, you could always subtract multiples of 2 pi. It wouldn't change anything. So the reason I say that is a time shift should be with the parentheses around the t and the time shift. Okay, this is a time shift, but it's a time shift, but this coefficient here is going to affect the actual time shift. Yeah. Okay, so it'll depend on the frequency. Okay, lastly, if you, there's a property, a differentiation. We talked about properties of the Fourier transform. In one of your problems out of the book, you're going to be using the property of the differentiation property. It's not one we've talked about. However, it is in the book. You can look it up, what the property is to solve the problem. It's actually quite nice. Remember, we had all of these properties of, like, if you time shift x, what happens to the Fourier transform? Well, you also have a property that if you take a derivative of x, okay, the Fourier transform of this is very simple. Assuming we knew that x of t had a Fourier transform capital X of f. Let's assume we're given that. Okay, then the derivative of x has a Fourier transform that's I 2 pi f times this Fourier transform of x. It's so simple. All right? And if we had more time, which we'll do next time, I guess, we'll derive it. Show you how you derive such a thing. Okay? It's very easy. You just plug in the formula for the inverse Fourier transform in for x, and you move the derivative inside the integral. You'll get it in a moment if you do that. Okay. And it's actually nice to interpret. It says that what have you done to a signal when you take a derivative? Well, the spectrum being capital X, the only change to it, this is all a constant, so don't worry about that, the I2 pi. What you've changed is for high frequencies, you've amplified them. For low frequencies, you've attenuated them. That's exactly what a derivative does. Maybe you've probably never thought of it that way, but that's what it does. All right? So it's kind of nice that you have a new way of thinking about what a derivative does. And so, yeah, you can use this in your problem set, and we'll revisit it.